Good morning, everyone. Welcome to this morning's Knowledge Bank. Today's webinar is going to be hosted by Jason Page and Thomas McCosker, who are Senior Sustainability Specialists at Ingleton Wood. They're going to be providing a presentation on sustainability and overheating in new buildings. If you have any questions throughout the webinar, please submit them via the Q&A button at the bottom of your screen, and we will try to get through as many as possible at the end. Today's webinar is also being recorded and will be available to watch back via the News on the Block YouTube channel. I'll also be sending a copy of the presentation. I will now hand you over to Jason to begin this morning's session.
Good morning. My name is Jason Page. I'm a sustainability specialist for Ingleton Wood. So I specialise in housing, particularly looking at the impact of new and upcoming standards and legislation. I also have with me Thomas McCosker, who is our thermal modelling specialist and certified passive house designer. So to kick things off, I'm talking about overheating. And how the new Part O overheating regulation is trying to reduce the impact in new homes. So I'm going to be covering a lot of ground in sort of a low to mid level, covering what Part O is applicable to, the criteria for the simplified methodology, and a simple case study. I'll then be handing over to Thomas for insights into the dynamic thermal modelling, SIBSI criteria, and future climate scenarios. So what is the issue with overheating? Overheating occurs when two things happen. Firstly, excess heat comes into the building, and secondly, we can't get rid of it. So we get excess heat generally when we have too much glazing in the building, and heat, both wanted and unwanted, comes in through sunlight. So I'm not going to go too deep into the science of that, but essentially infrared radiation comes through the glass, it loses some of its energy and the wavelength shortens. Once this happens, it actually can't get back through the glass, trapping it in the room. So the trick to reducing the energy getting in is not to let it in the first place. So that's whether that's by using external shading, shutters, smaller windows, etc. But if you can't effectively stop all heat getting in, that will require you to be in a solid box with no windows. So the second part of it is getting rid of the excess heat you have required. So this is achieved through ventilation, whether that's through passive stack, through windows on different floors, cross ventilation with windows on opposite sides of the building, or through more modern methods such as mechanical ventilation or MVHR. But why is this a problem now? Well, traditionally we've designed our buildings to hold on to heat. We all want the free heating as much as we can. We value the solar gains in winter, so we don't have to run our boilers as much. However, for traditional summers where it's hot during the day and cool during the night, we were able to purge most of the heat out of our home. But with the summers we've been having and the summers we're projected to have, with getting up to 40 degrees last summer, with no reprieve overnight for prolonged periods, it's a recipe for all our buildings to fail because they're simply not designed to cope with that scenario. So we need to start designing buildings to mitigate against overheating during the summer, as well as retaining the heat during the winter. And this is where Part O is attempting to influence, challenging the way that we design homes. So Part O came into force June last year. However, with all the regulations at the time, was covered by transitional arrangement. This is meant to only a handful of projects that actually have fallen into the regulations so far. This changed in June this year when it came fully into force. Basically, anything that's designed now needs to be fully compliant with Part O. And first and foremost, this is a domestic regulation. It covers any type of building or home that is used for domestic purposes. So that's homes, student accommodation, care homes, residential homes, anything of that sort of ilk. There are two main methods of compliance with Part O. The simplified method is what I'm going to concentrate on here today. The simple method ignores a lot of building science, such as thermal mass, insulation levels, mechanical ventilation systems, in favour of getting the basics right. So it's about getting your foundations right so that the building shouldn't overheat. And the dynamic thermal modelling method, Thomas will go through this a little bit more later, but essentially this method allows a lot more flexibility than the simplified method, allowing you to take in those thermal mass, insulation levels, etc. into account. But it's a double-edged sword, because building a more accurate representation of the building, with that comes time, expertise and costs. And if you're waiting till building regulation stage, where you would probably think you would need to look at this, you're probably too late. This needs to be looked at pre-planning when you're designing the buildings. And at that stage, the dynamic method, it's quite a lot to achieve, and it may not be viable on most projects, because maintaining an accurate model on a changing design is going to be very challenging, potentially expensive, and potentially quite a prolonged procedure. So if you are looking at a site, I would advise you to lean quite heavily on a simplified method if you can. At the early stages at least. So it's called the simplified method, but to be honest, it's anything but. So to get into it, there are two main criteria in the simplified method. Limiting solar gains, so this is making sure you don't have too many windows, and removing excess heat. So that's making sure that the heat that does get in can be expelled through ventilation. So this is addressing both parts of that overheating equation. So the criteria you need to comply with is governed by two factors, which is determined in table 1.1 of Part O, and that's what is shown on the screen here. The first is whether you have cross ventilation. So this is whether you have windows on opposite sides of the building. Windows on adjacent sides do not count. This means that in particular corner flats will have to comply with more stringent criteria. So if you can, you want to design for cross ventilation to have an easier ride through Part O. The second is whether you're in a high risk area. Basically high risk is London and some postcodes in Manchester, but basically everywhere else in England is a moderate risk. This factor doesn't necessarily mean it's hard to comply in a high risk area, though. In some situations, it can be less onerous to comply in high risk, albeit with some caveats. I won't get too far into this, but it can be worth remembering that you could have the option to use high risk even if you're in a moderate risk area. So you go through and you select your table. You have a set of compliance values for the two criteria. So what we are going to be looking at is the orientation with the biggest amount of glazing. That's going to determine the maximum amount of glazing you can have in both the building and the most glazed room. So if your facade with the most amount of glazing is the east, you can have up to 18% of your floor area as glazing in the building, and up to 37% of your maximum glazed room floor area as glazing in that room. So if you have a house type that is repeated, it may not comply if it is orientated in a different direction, unless you've designed for the worst case, which is usually the west face and facade, where you're only allowed 11% of the floor area's glazing. And that can be not a lot. So the next part is the ventilation criteria. Again, they are separated by whether the building is high risk or moderate risk, and whether there's quad ventilation or not. So this determines the figures that you use. So for ventilation, we again have two targets. The first is that the free area, so that's the size of openings that air can move freely through as a percentage of either the floor area or the glazing area, whichever is greatest. This is essentially a daytime criteria. So in real terms, it's saying if it's hot, we are throwing all our windows and doors open and seeing how much air we can get out of the house. The second is the bedtime criteria, bedroom criteria. This is a nighttime criteria. So we are assuming that people are in bedrooms at night and that they need to cool down. So we are literally just concerned with what people can do with openings in the bedroom at night. So unfortunately, that's not as easy as it gets. There are a couple of criteria that temper what we can use as openable windows and do potentially affect design choices. So firstly, we have noise and pollution issues. So this is where you have sites which are near major roads or near loud noise sources. You are likely to need to reduce the number of windows that can be opened as part of this strategy or discount them altogether. It's highly likely in this scenario that you'll be pushed towards a dynamic route, simply because you won't have enough openable windows to pass the ventilation criteria. The second part is about security. So security applies to the bedtime, nighttime, I will stop calling it a bedtime, bedroom nighttime criteria. So here, if a window is openable, then the regulations say that it must not be accessible by an opportunistic burglar. So in real terms, that means that ground floor windows and any windows above ground floor roofs, garages or porches or anything like that, cannot be included in the calculation because they cannot be opened safely without being opened a target for an opportunistic burglar. So this makes bungalows and ground floor flats incredibly difficult to pass on first principles. For the nighttime scenario, we can use restrictors to make the window secure, but often we found this doesn't provide enough ventilation for the bedroom ventilation criteria. But there are a couple of potential options here, and they all involve challenging our architectural norms. So firstly, you could consider external security bars or grills. Quite frankly, they don't look great, but they are fairly standard in countries where cooling is a priority. Internally, we can use sliding or removable security options. Shutters look a lot better and are actually recommended in Part O, but the problem with these is they reduce down the free area significantly. So external shutters are even better as they prevent solar radiation getting through the glass in the first place, but they switch us to using inward opening windows, which again is not the norm for us. However, hold on to that thought with inward opening windows because it's an interesting conversation. Or ventilated louvered panels. So these can be installed next to the window or above them or anywhere in the wall, quite frankly. They can be opened from the inside and give ventilation without leaving an opened window. This is probably the neatest option, but again is a completely different aesthetic than we're probably used to. Next, we have protection from falling. There are a couple of criteria here, and this applies to any floor where the floor change in height between the inside and outside is greater than 600 mil. So all upper floors will fall into this, and some ground floors if there's significant changes in levels. The first is that window handles cannot open more than 650 mil away from the inside face of the wall. So with a typical 350 mil wall, that means windows can only open to about 300 mil beyond the external face. This gives us a max opening angle that we can use for windows without the occupant having to lean out to either open or close the window. That significantly reduces the amount of free area that we can get ventilation through. But on upper floors, we can potentially get around this by using, by looking at things like inward opening windows. Any tilt or turn windows opening inwards would have its handle internal and therefore would comply with 650 mil beyond the face of the window, beyond the face of the wall. Therefore, we'll be able to open it to 90 degrees and get full ventilation through that window. Good news for ground floor, which is rare. You can assume that windows can open to 90 degrees and all doors except the front door can open to 90 degrees, so you can have full ventilation. The second part of this is that any glazing less than 1.1 meters from the floor must have guarding to stop climbing. So this is clarified as being plus or minus 100 mil, so it's effectively 1 meter above the floor level. So this can be solved through fixed bars, fixed panes at lower levels, or higher level windows. This does potentially have the ability to conflict with fire egress windows and fire regulations. So you do need careful thought to make sure you're ticking all the regulation boxes. So that's a very quick, as I say, high level overview of Part O. I'm just going to bring up a very quick case study where hopefully I'll show you how that's working in a real life. So this was a site in Norfolk, so was a moderate risk. However, it consisted of a lot of bungalows that have a large amount of glazing. So looking at the floor plans and elevations, the west and the south elevation, so this being the south and the west elevation, have large amounts of glazing. So running the building through the calculations, we failed on a number of criteria. What we found was the south had the most glazing, which meant our target, according to table 1.1, which is here, required a maximum glazing area of 15% of the floor area of 15%. So we had to remove glazing to get the target down. There's no two ways about it. So prime candidates were the large patio doors on the south-facing facade. Having removed those windows, though, the most glazed facade actually switched to then become the west, where we hadn't touched the windows. So we've reduced the glazing to below 15, but the west is now the it's the biggest facade for windows, and the west criteria is you need to be below 11%. So we still fail Part O. So we needed to balance removing windows with maintaining the amount of glazing on appropriate facade to mean our target was high enough to pass. We also didn't pass the daytime ventilation criteria. We had a number of fixed lights on each window, which obviously doesn't contribute to ventilation rates. So what we did is we evened up the windows and made a much greater area of each window openable, which was enough to bring us to a pass. And finally, on bedrooms, as we were in bungalows with windows open to the public realm, they were not secure. So we had to use options of security systems, or our solution was that we used tilt and turn windows in the bedrooms. This meant that we can use the window as fully openable for the daytime criteria, but use the tilt function at night to provide a greater opening than restrictors would, but give a greater opening area for the ventilation criteria for the nighttime situation, while maintaining a secure window. And this is the result. And whilst the glazing is significantly reduced, the building still has a good amount of glazing. So to conclude, I would run simplified calculations at an early stage as possible when designing. The earlier you are, the greater the opportunity to design out some of the issues. If at all possible, avoid ground floor units. Bungalows and ground floor flats, they have particular design challenges in bedrooms in the simplified method. If this is not possible, then you do need to consider design solutions. There could potentially be an argument that windows on the ground floor in private secure spaces are not open to an opportunistic burglar. This is an interesting argument and not one I've tested through building control myself, but it could be worth a conversation at an early stage. As if you can design your single-story buildings with bedrooms only open to private garden, that could potentially satisfy this element. Otherwise, you will need to consider security bars, secure ventilation options. Upper floor windows need to be designed against falling. This could be inward opening windows or fixed lights at a lower level. It's worth remembering that only windows required as part of the opening strategy need to be included in this. So if you're over the requirement with other windows, you can discount the problematic ones. So they wouldn't necessarily have to comply with a garden specific to Part O. So if you've got a nice big window that you want to open, as long as you can pass Part O without including that in the ventilation criteria, do what you like. The garden issue does not come into play. Outside Part K, of course. Also, for most projects outside of London, we're going to be in a moderate risk area, but it's worth saying that we do have the option to move to high risk if we want. That changes some of the criteria, but in some cases, particularly where the most glazed facade is west facing, it can reduce the targets. It does that because in addition to the criteria, you have to include some form of solar control. This can be external shutters, brise soleil to block out 50 degrees of sun on the south elevation, or my favorite, which is changing the glazing spec to a minimum G value of 0.4 and a max solar transmittance of 0.7. So if you really are in a bind, that can be quite a creative solution. And in one case we looked at was actually a viable option. However, it's also worth remembering that as it changes the targets for the glazing, it changes the targets of ventilation too. And they generally do get worse. So you could end up solving one problem and creating another. And lastly, I would treat dynamic thermal modeling as the catch-all solution if you don't like what the simple methodology is telling you. It allows you to be much more flexible, but don't think you can design anything and get away with it. It still requires good solar control principles in place. So with that in mind, I'm going to finish here and hand over to Thomas McCosker to talk about this and give you a bit more detail. Thank you.
Hello all, thank you for coming today. And yeah, I'll jump right in with my presentation, hopefully. Right. So as Jason said, dynamic thermal modeling is a last resort. However, I will caveat that by saying it doesn't necessarily mean it's going to work. It is a last-ditch effort. It does add a lot of details and therefore a lot of complexity to a design. But all those details can come back and bite you. If you have those high levels of glazing, they're still going to be accounted for in the dynamic thermal model. They're just going to be accounted for a bit differently. And that might be a good thing, but it also could be a bad thing. So again, we got our front page. There's our lovely faces. And so I'm going to be covering the dynamic thermal modeling side of part O. And I will touch a little bit at the end on TM52, which is the commercial side of thermal modeling. Mostly because we said we'd do that in our headline for the CPD. And also, as I'll show you a little bit later, all of these methodologies are tied together in one way, shape, or form. As with Jason, we're going to touch on a couple different things here. I'm going to talk a little bit about the background of dynamic thermal modeling, how we need to demonstrate compliance, methods for achieving compliance, summary, and then a little bit of future considerations, looking at our changing climate and why that's a problem for us going forward. As Jason mentioned, the simple method for compliance with Part L is a much more cost-effective way to do this because as he said, it's not a simple method, it's just a simpler method. If compliance for a simple method cannot be achieved, a dynamic thermal model must be run. Although, as Jason was saying before, it might be better to change the design and get that simple method to pass because it is expensive and very detailed, this dynamic thermal modeling. Part O has largely been based on TM59, which is on the right side of the screen. This is a methodology for the assessment of risk in overheating in homes. It's developed by CIBSE, and which is also largely based on TM52, which is the commercial version, looking at overheating in non-dwellings, I mean, buildings. In much the same way, a simple method looks at the building geometry to complete an assessment. A dynamic thermal model looks at this stuff as well, but it does it in 3D in a design software. So here we have a couple of screenshots of what a dynamic thermal model might look like. We've got some glazing assignments. We've got the general geometry on the left, and then we have profiles. That's something that doesn't come into the consideration in the simple method. On top of this, internal gains have those dynamic gains to make sure that the solar gain that Jason was talking about isn't getting augmented and bolstered by an internal gain, like a kitchen that's being used in the afternoon as the western sunlight is pouring into a lovely kitchen. The TM59 methodology is a prescriptive methodology, which means that it has certain gains you must account for within each occupied space. The gains and their allowances have all been based on the DECC's Household Electrical Survey. A TM59 model must use these gains and the profiles associated to illustrate how the building is likely to perform under the tested weather conditions. Part O has adopted this TM59 methodology largely in its entirety. There are some minor amendments which are mostly just this window opening augmentation. Based on, let's see, as we see in the section B there, it does make sense largely. So at night, for example, a window at night between 11 p.m. and 8 a.m., the windows must be open. If the temperature in the room is above 23 at 11 p.m., the occupant's going to open the window because they're warm. And they're not going to close that window again until 8 a.m. when they wake up. Most of us get up a bit before that, but that's how the methodology works. So it looks at occupancy profiles, it looks at typical usage patterns and tries to replicate that within the the methodology and the design profiles. Limiting solar gains is also a big difference between TM59 and Part O. As Jason mentioned before, the strategy doesn't change too much between the simplified or the simple and the dynamic options. We're still talking shutters, external blinds, overhangs, awnings. But in TM59, we used to be able to use internal blinds. That is no longer the case with Part O. You're no longer allowed to use internal blinds as part of your methodology. TM59 did have a caveat saying that you had to say if you use internal blinds in your thermal modeling report, so that if they did get VE'd out and people complained about the temperature, they could go back to the report and say, actually, well, you have to include the blinds. This change in Part O to not allow blinds did cause a bunch of headaches this last year, and I'm sure we'll see those again, where previous designs or archived home designs that used to pass fine under TM59 no longer pass Part O because we can't allow for those internal blinds. Presumably, Part O thought that blinds are easy to VE out or they're not used appropriately by occupants. The conversation can go back and forth, but it is worth noting that in your design, it has to be an external shading device, or as Jason was saying too, the size, the orientation, or the solar transmittance, that G value that we see in section BII there. Part O has the same criteria to demonstrate compliance as TM59. You have to pass criterion 1 based on TM52, which I'll go into in a second, and also a bedroom test, much like Jason was talking about before. The two assessments look at internal temperatures within occupied spaces to ensure that occupants are comfortable during the day, but also at night. The first assessment is taken from TM52 and looks at the number of hours the operative temperature, which is the temperature inside, exceeds the threshold temperature for the season. It's worth noting that it is a threshold temperature, it's not a fixed temperature. So because people are able to tolerate warmer temperatures in the summer than they are in the winter, that fluctuates depending on the external temperatures and the design conditions do. The second assessment is a bedroom test to make sure that people are able to sleep comfortably all year round. And this assessment looks at the internal temperatures of a bedroom. They may not exceed 26 degrees C between 10 o'clock at night and 7 in the morning for more than 33 hours annually. That's a really important number to remember, as we'll touch on it in a minute. But because some future weather files don't even have that outside, let alone allowing for that inside. Appropriate weather files must be used. We had high risk and high risk areas for the simplified method. This has dedicated weather files for certain areas, and the appropriate weather file has to be used and demonstrated that it has been used within the thermal modeling report. These weather files are DSY files, or design summary years. There's 14 of them spread out across the UK. A couple of them are in London. So that's TM59 in a nutshell. As Jason was, all of these have to comply with the same regulations and design considerations that Jason mentioned earlier. That's going to be the security, that's going to be the internal, the window opening degrees and everything else. So this is a logical step to do following a simple method, because all of those theoretically have already been set out by the design team. It's just a matter of putting them into a dynamic thermal model and bringing that into fruition through a number of hours of dedicated modeling. The TM52 is that second piece I was going to talk about, and it forms the background of TM59, and it also, which in turn forms the backbone of Part O. TM52 is for non-domestic buildings and is much less prescriptive than TM59. The appropriate gains must be modeled, therefore, which has to be determined by the design team based on the equipment, the occupancy, the lighting, rather than the prescribed TM59 gains that we have in the other methodology. To demonstrate compliance with TM52, two of these three criteria here 1, 2, and 3 must be met. And those can be onerous, especially in these future weather files that we're looking at right now. As Jason mentioned earlier, there's also a number of ways to achieve compliance through different design options, but there is no silver bullet to guarantee that this will pass. And as I mentioned, dynamic thermal modeling is not that silver bullet, and a design decision is also not a silver bullet. We have a number of things that can drop this down and help with the overall performance, but there is no silver bullet, unfortunately. It's just going to take work and careful thought on the design. So the first one to consider is thermal mass. This isn't included, or this isn't considered in the simple method, but thermal mass is generally a dense material such as concrete, stone, or brick. Water is also a good example and can also be used in greenhouses. So utilizing thermal mass or a thermally responsive material can have a dramatic effect, as we can see here on the left. The red line is the external temperature. The orange line is a predicted internal temperature with a lightweight construction, and that blue wavy line is the predicted internal temperature with high thermal mass. As you can see, that thermal mass just regulates that temperature. It brings down those peaks a little bit, and it also shifts the peak temperature outside of the external peak temperature. So when it's really hot outside, it's not quite so hot inside, but it might peak a little bit later in the evening, say, when the outside temperature is a bit lower. And which also brings us on to the ventilation side. We really have to make sure that that ventilation is able to purge the heat that we're gaining. Thermal mass does equalize the temperature, but it also rejects that heat back into the space. Dynamic thermal modeling takes that into account. And so you can see a benefit of including a massive floor system or a thermally massive ceiling, or in some cases, people include thermally massive internal walls. The problems with thermal mass is that the absorption can be saturated, as many of us have experienced. This absorption, the saturation can be. A good example of it is last summer in the heat wave. A lot of our houses are older in nature, and at the beginning of the heat wave, they're generally tolerable. The brick or the masonry is absorbing that heat, but at some point it becomes saturated, which is why at the latter part of the heat wave, oftentimes we're all sweating, we're all uncomfortable, and we all wish there was something else we could do. Managing your thermal mass is a high priority, and that can be effectively done through ventilation. So utilizing proper ventilation techniques to purge the absorbed heat at night when the temperature is lower, and therefore put stored cooling into those thermal components, is a really good option. Ventilation can be natural or mechanical, so you can have natural ventilation, as Jason was describing, with the cross ventilation or single-sided window openings that we were talking about before, as seen here on the right. It has to allow that free movement of air, though, through the space during both day and night. So those nighttime restrictors or the daytime restrictors have to allow for sufficient air to come through. Mechanical ventilation can also be used to great effect. Heat recovery has been shown to benefit the spaces in the winter. It's also the case in the summer. So you're able to recover that cooler internal air and temper the incoming hot air with that colder air. And I'll talk about this little graph in the bottom left in a second, which illustrates that. It's important here that for natural ventilation, that nighttime ventilation can be employed, and it is particularly important that a summer bypass option for an MVHR system is to be fitted so that we can bring in that cold nighttime air without tempering it. So if you look in the bottom left here, we can see that the intake and exhaust temperatures are relatively high and track with each other. And then as those come through a heat recovery unit, the internal temperatures that are being brought out are tempering that external air and bringing them down to a more tolerable level. So just as a note, On the left-hand side there, that graph is in Fahrenheit, so don't get too concerned. This is a Fahrenheit. We're not at boiling point here with these temperatures in Italy. But also you see in the evenings, those dips in external temperature, those can really be brought in really easily with that, that summer bypass, which is represented here. So the air doesn't go through the heat exchanger, it goes around it. So you're able to bring in that cold nighttime air and supercharge your thermal mass, or just cool down your space so you're ready for another hot day the next morning. Limiting solar gains is another great thing. Hopefully I'm not hitting a nail on the head. Jason already discussed this, but external shading devices are the best. They cut down on the solar gain before it even enters or hits the surface. A window that is hot still radiates heat into the space, but if the sun doesn't hit the window, then it doesn't radiate the heat in. There's a number of shading options on the right there that are really well outlined in Guide F, which is helpful. And a good example of tinting or solar thermal control can be seen on the left there, where different percentages have been put on sequential windows. The other things to consider here are organizing your internal layouts so that high solar gain areas like the south and the west aren't impacted quite so much. So maybe organize your bedrooms to be on the north side so that they won't get heated before you go to bed and the bedroom tests don't fail. Think about your living spaces and how those are organized within the site. That can really help. Reduce the amount of glazing. First and foremost, as Jason was saying, if you don't have the glazing there, then it doesn't let the solar gain in. Shading is highly important. And then finally, those the solar control films are also really helpful. Insulation is also important here. We always think about insulation in the winter, we're trying to keep the heat in, but it also works the other way around. In its most basic form, insulation just reduces the flow of heat from one area to another. So if it's hot outside, it doesn't get quite so hot inside because of if you have a good thermal shell to your building. By using high levels of insulation, we can manage that temperature better. We can decrease heating loads, and also the external conditions don't translate quite so well. In my mind, it's always better to improve on the existing building regulations, even the new ones, by 10 to 20%. It's always good to increase that even more if possible within the budget. But we all know budgetary constraints can be tricky to negotiate. And finally, we have infiltration. Good air tightness is important, not only for temperature, but also for pollutants. Infiltration essentially is the uncontrolled movement of air through a building fabric. This can be seen in the images on up here. And it allows for external untreated air to come into the building, affecting the amount of heating that is required, but also increasing summertime temperatures. Infiltration also brings external pollutants in the existing surrounding areas into the building. And so minimizing that has at least two purposes. Infiltration largely occurs with areas where poor sealing has taken place or detailing. And the best way to prevent unwanted infiltration is to target good, and that means low air pressure tests results for your buildings, and ensure the building details are appropriately done so that the builder knows exactly how it's going to be done on this project. So in summary, 5 considerations can help pass, but don't necessarily guarantee a pass for dynamic thermal modeling part O, and also helps for TM52. You'll note that some of these key points are exactly the same, or at least very similar to the ones Jason laid out earlier. I've kept them in because there are different considerations with the dynamic model than there are with a simple model, or a simpler model. Sorry, Jason. It is still quite a lot of work to run a simple model for overheating in part O. And finally, we all know and acknowledge that climate change is an issue that we all face in the UK and around the world. We're seeing rising global temperatures, as the graphic here shows, and last summer demonstrates what a typical, or sometimes even a, depending on which weather file you're looking at, a low heat summer might look like. Whilst TM59 and TM52 and Part O don't require you to pass future weather scenarios or more extreme weather scenarios, we do have a lot of clients that are looking at running those stress tests to see how a building will perform or theoretically might perform using future weather files to make sure that a belt and braces approach is coming in and we're not going to be fitting AC units in a couple of years. As the climate is warming, future weather conditions are getting more and more difficult to pass with the overheating methodologies. The DSY weather files that we have currently have predicted future weather files looking at 2050 and 2080. And summers that we had last year are going to be the norm, if not even worse. The problem with overheating assessments is that we're seeing it is that future weather scenarios, often the external temperature is warmer than the methodology allows for internally. So what I'm saying is that an external temperature is going to be warmer than the methodology allows for it to start with. So even if you bring in that external air during the day, you can't get the temperature inside down any further, which is why we have to think about these interventions, those 5 things I mentioned earlier, with the thermal mass, with the ventilation, integrating those two together, minimizing solar gain, having a really concerted effort on trying to reduce the load in the building, reduce those internal gains and reduce the temperatures first and foremost, so that we can use that cooler nighttime air, even if it's only a couple degrees cooler, to just bring that whole mass down and allow for a cooler temperature during the day. The graphic in the lower right shows the difference between a 2080 weather file in London and a 2020 weather file in London. We can see that generally in that summer season, it is just a couple degrees warmer across the board. And that is a make or break for a lot of these models and a lot of these designs. 2 degrees can just mean a fail and things have to go back to the drawing board. So that's the end for me. Sorry to leave it on a bit of a downer note, but it is what we're facing. And I think, Jason, you probably would agree with me that building regulations will start taking into consideration these future weather files. We don't want to be designing buildings that only work in a 2020 weather file or only work in the high risk areas in London as an extreme. We want to be able to future-proof these designs so that as they go through their lifespan of 60 years, which is the normal lifespan apparently for a building, we don't experience overheating on a massive level going forward.
Yeah, I think that's a mistake that we have made in the past, and through the design of buildings, we've not been looking at the future, which is now where we are experiencing these overheating events, and our buildings just haven't been designed to cope with it. If we're designing just to current weather patterns, we do risk doing that again and having buildings that are inadequate for future scenarios.
So it looks like we have another 12 minutes.
So we welcome any questions. I see one. Do you want me to?
Yeah, there's one here. I think it was referring to the regulations that you were talking about earlier, Jason. It just says, do these regulations apply to the older buildings, for example, Victorian or Georgian houses, which have been converted into flats?
The easy answer to that is Part O does not apply. Part O is for new build residential type buildings. Any conversions you're doing, any extensions you're doing, anything under permitted development where you're changing offices into residential, Part O doesn't apply. You could probably levy a criticism that it should do, considering that they're going to overheat in exactly the same way, and why shouldn't we be applying that? The caveat I put on top of that, though, is if you're anywhere near London, the planning authority may ask you to comply with TM59 and provide an overheating report. So essentially, they will be asking you to comply with the regulations, but they will be through planning rather than through regulation.
And it should be noted that what we've talked about today is national planning policy. Local districts and local councils may ask you to do other things. They may ask you to run future weather files going forward. What we've talked about here is the national Part O policy. And going forward, be mindful of any local planning restrictions because they can be more onerous and they do change much more frequently than a national policy will.
Okay, thank you. We've got one more question. If there was a new development on an already existing building or a new floor, would Part O apply?
I think it would. If I'm understanding your question, you're asking if you put a new floor on top of an existing building,
I think that's what I mean.
That would count as a new construction. Therefore, your new Part L would apply as a new build, and therefore Part O would apply as a new build as well.
Okay, thank you. I think that's it. Yeah, Amy was just saying thank you. Yeah, that's it. We have no more questions. So I think we can finish up there. Thanks, Jason. Thanks, Thomas, for both of your time today. Thanks to everyone who's joined us. As I mentioned earlier, a copy of the slides will be available later, as will the recording. If you want to join any of our other upcoming webinars, please take a look on the News on the Block website. Our next webinar is going to be next Tuesday, where Brevetons are going to be discussing arrears recovery. Otherwise, thank you very much for joining us and enjoy the rest of your day. Thanks, guys.
Thanks all.
Thank you.
Take care.
Bye.
Cheers. Yeah. Bye.